Hello YouTube, this is Wenn who does research for fun. In this video, I would like to go over my first authored paper titled GNSS-IMU-Assisted Colored ICP for UAV-LiDAR Point Cloud Registration of Peach Trees, which was published in the journal Computers and Electronics in Agriculture in 2022. Ever since I played with Logitech webcams and Velodyne LiDAR during my master's program, I became very interested in computer vision research. Images and point clouds are just visually appealing, stimulating, and satisfying data to process. I can't remember when and how, but I stumbled upon the concept of SLAM, or simultaneous localization and mapping, maybe on a MATLAB tutorial webpage. It was so cool to see a geometrically consistent large-scale point cloud map being generated in real time. Therefore, I always wanted to do some research along the lines of SLAM. During my PhD, I used a DJI Matrice 600 Pro for my research, which does not have a very accurate GNSS and caused imprecisions when I tried to georeference point clouds. I attempted various SLAM algorithms to register point cloud frames, but didn't really get the results I wanted, since I observed that there were very few usable features in nadir view orchard point clouds. Therefore, I had to come up with my own unique solution, and thus the idea of the paper was born. Considering its complexity and sophistication, I attempted to submit the paper to the top 2 journals in the remote sensing category. One was Remote Sensing of Environment, and the other was ISPRS Journal of Photogrammetry and Remote Sensing, and I received instant rejections from both journals. Eventually, we went for the best agriculture-oriented journal, Compag, and had the paper published successfully. Now let's dive right in. Unmanned aerial vehicles, or drones, have been extensively deployed in agricultural studies in recent years. The high-resolution, remotely sensed crop data can be valuable for both farm management, such as crop monitoring and weed detection, and agronomic research, such as plant phenotyping and plant trait modeling. Current off-the-shelf UAVs have advantages such as low cost, compact size, robust hardware, and user-friendly software, ensuring flight and data collection flexibility. Aside from the common payloads, including RGB cameras, thermal cameras, multispectral cameras, and hyperspectral cameras, LiDARs emerge as another instrument that are being often installed on a UAV platform. LiDARs are capable of actively gauging distances, commonly utilizing near-infrared lasers based on the time of flight or phase shift principle. Because of their ability of generating high-resolution point clouds in real time, LiDARs show promising potentials in plant 3D structural reconstruction and are considered as the next-generation plant phenotyping technology. The application of UAV-LiDAR systems in plant-related studies started to boom in the past 2 to 3 years before the paper was published, since remote sensing-based methods have the natural advantages of scanning large areas, such as agricultural or forested fields, with low time and labor costs. Many agricultural studies have experimented with directly estimating or indirectly predicting plant parameters with UAV LiDAR systems while using manual measurements as ground truths to assist timely crop management. Some of the investigated examples include crop height, lodging self-recovery ability, leaf area index, above-ground fresh weight, biomass, and crown area. Since a LiDAR measures distances relative to itself, when the sensor is in motion, such as being mounted on a flying UAV, additional sensor inputs or point cloud registration techniques are required to align raw LiDAR data. The first and most common method for LiDAR data alignment is GNSS and IMU-based georeferencing. GNSSs are able to locate receiver positions continuously worldwide utilizing radio signals from at least 4 satellites, while IMUs measure attitude angles via built-in accelerometers, gyroscopes, and sometimes magnetometers. There are a few error sources that can affect georeferenced point cloud quality. The first one is GNSS positioning error. Standalone GNSS positioning is unable to pinpoint locations with accuracies better than a few meters. and GNSS signals can be obstructed by trees, buildings, bridges, etc., which leads to reduced positioning accuracy. The second one is IMU measurement error. IMUs often suffer from drifting or accumulative errors and are not suitable for long-term position tracking. The third one is sensor synchronization error. To improve point cloud georeferencing, real-time kinematic and post-processed kinematic are two popular methods for improving GNSS positioning accuracy, which are based on DGNSS positioning and requires ground-based reference stations, while tactical-grade IMUs can be employed to minimize drift, although both solutions can be expensive. Alternatively, point cloud registration algorithms can align LiDAR data even under GNSS-denied conditions, while SLAM, or simultaneous localization and mapping, refers to frameworks that are able to construct and update geometrically consistent maps in an unknown environment at real-time speed with point cloud registration algorithms integrated. SLAM is a fundamental research area in robotics, as it is promising in solving challenges related to autonomous navigation of artificial intelligence robots. Different sensors can be utilized within SLAM methods to map environments and ascertain robot poses. Some exteroceptive sensor examples include LiDAR, sonar, monocular camera, stereo camera, and RGB depth camera. Some proprioceptive sensor examples include odometers and compasses. At the time, a few studies in existing literature tested SLAM algorithm in forest environments. One research group proposed to use olive tree stems as landmarks for ground-based graph SLAM, and later they stated that the SLAM algorithm was able to improve treetop volume estimation in a different study. Another research group tested 4 state-of-the-art monocular SLAM systems, which mostly failed producing usable forest maps. There are a few challenges that hinder the application of SLAM in agricultural studies. First, regular indoor geometric point cloud features such as lines, corners, planes, spheres, etc. are involved in many LiDAR SLAM algorithms for solving data association, yet they are often missing in outdoor agricultural settings. Second, unique agricultural landmarks such as tree stems might be blocked by tree branches and leaves from nadir view LiDARs. Therefore, they are not appropriate for aerial SLAM applications. Last, SLAM algorithms can have inconsistent performance under complex environments, which might explain why SLAM applications in agricultural studies are still rare despite being more economical than survey-grade GNSS. The study was motivated by the fact that few studies in the literature at the time explored utilizing built-in navigation units of UAVs for LiDAR data registration to help lower equipment costs and limit UAV takeoff weights, and very few studies had a focus on improving SLAM specifically for agriculture. The goal of the study was to explore a point cloud registration methodology that can be applied for aerial LiDAR data of agricultural fields and potentially serve as the foundation of a SLAM algorithm. However, the study scope was limited to single-pass LiDAR data from flights with straight paths. Specifically, the objectives of the study included: first, develop a low-cost UAV-LiDAR system with a single-board computer and UAV's built-in navigation sensors such as GNSS units and IMUs. Second, propose a point cloud registration algorithm that is tailored for aerial LiDAR data of agricultural environments such as orchards. And third, evaluate the performance of the proposed algorithm for plant parameter estimation in comparison to GNSS and IMU-based point cloud georeferencing. Now let's get into the UAV LiDAR system development. First, let's talk about the components of the system. The UAV platform chosen for the study was Matrice 600 Pro. It had a 6 kg payload capacity and could complete 15-minute flights even with a LiDAR and an external power source. The UAV was equipped with DJI's A3 Pro flight control system. It featured 3 sets of GPS Compass Pro modules and IMUs, out of which 2 sets were manually disconnected in the study to keep the lever arm offset between LiDAR and GNSS antenna constant, and it allowed the UAV to hover with plus or minus 1.5 and 0.5 meters horizontal and vertical accuracy. The A3 Pro was also compatible with DJI Onboard SDK, which enabled users to retrieve onboard sensor readings such as GNSS and IMU data and control the UAV with customized programs in an onboard computer. The LiDAR scanner employed on the UAV was Puck Lite. It recorded distance and reflectivity information through 16 lasers with a 903 nanometer wavelength and had a vertical field of view of 30 degrees with a 2-degree resolution and customizable horizontal field of view range and resolution. The sensor could take up to 578,688 laser measurements per second with a plus or minus 3 centimeter range accuracy. A Raspberry Pi 4 Model B was selected as the low-cost onboard computer that communicates with the UAV and the LiDAR. The computer had a 1.5 GHz quad-core processor and 8 GB of RAM. A 128 GB micro SD card was used for operating system loading and data storage. A BP101 power bank was used to power the LiDAR and the computer simultaneously, which provided both 12-volt and 5-volt DC outputs with a 21,000 mAh capacity. This table here summarizes all the key hardware specifications. The LiDAR was mounted on a 3D printed plate so that its lasers pointed straight towards ground during data collection, and the rest of the system components were installed on the UAV through a piece of steel sheet that could be attached to and detached from the UAV bottom via mounting brackets. The picture on the right also shows the complete UAV LiDAR system with 2 sets of GNSS units disabled. Putting together a UAV LiDAR system that can generate geo-referenced point clouds from scratch was not easy at all, and I really should have given myself more credits for that, since at the time, there were a very limited number of studies that reported customized UAV LiDAR system like mine. I remember I and one of my lab mates went to Home Depot looking for parts to fix the battery onto the steel sheet that the LiDAR was mounted on, and right after we walked into the store, we saw a big box of spring clamps for sale. I grabbed one, squeezed it a few times, felt it had a really strong grip, and it fitted the battery perfectly. So I just decided on the spot to use the clamp on my UAV LiDAR system. We were both laughing since a big old-fashioned clamp does not really match the style of a fancy state-of-the-art flying vehicle. But who cares about how it looks as long as it works great? As you can see in the left picture, the clamp sticks out beyond the drone perimeter like a little tail. Coincidentally, inside the big protective case where the drone was stored in, there were cut-out foam layers to fit the drone exactly and tightly to achieve max protection. For some reason, one of the foam layers had a small square notch cut out of it at exactly where the clamp would be when the drone was stored in the case, and the notch fitted the clamp tail perfectly. It almost felt like the case manufacturer already knew that we would install a clamp with what size at what location on our drone. The VLP-16 LiDAR was able to provide a 360-degree horizontal view utilizing an internal motor. We defined LiDAR data belonging to the same motor rotation from 0 to 360 degrees as one LiDAR frame. As the LiDAR would never remain perfectly stationary during data collection, theoretically speaking, unique GNSS and IMU measurements are needed for every single LiDAR point's georeferencing. However, considering the low UAV flying speed during our flight missions and UAV hardware limitations such as GNSS update rate, in-frame LiDAR motion distortion was ignored in the study. To mitigate the distortion, the LiDAR motor was configured with the fastest rotational speed, which was 1,200 RPM, and corresponded to a 0.4-degree horizontal resolution. The horizontal field of view of the LiDAR was configured as 135 to 225 degrees, since our aerial application implied that the LiDAR would always be above target plants. Additionally, background data from objects above the UAV such as insects and birds would be ignored, and the field of view mimics many solid-state LiDARs, allowing us to indirectly evaluate the generalizability of our proposed algorithm for alternative LiDAR brands and models. The LiDAR was configured with dual return mode, which recorded the strongest and last returns from each laser firing. The LiDAR and the onboard computer were connected via a Cat6 Ethernet cable, and the data transfer between them was completed through user datagram protocol. For each flight, all collected LiDAR data were saved in a unique PCAP file. The A3 Pro was connected to the onboard computer via a USB to TTL serial cable. After setting up the software environment in the onboard computer for OSDK, a customized C++ program was used to access A3 Pro telemetry data, which were saved in a TXT file at 50 Hz during data collection. This table shows the descriptions of the telemetry parameters. The onboard computer had an Ubuntu Mate 20.04.1 operating system, which was responsible for controlling data collection through customized bash programs, as well as storing all collected data. The synchronization between LiDAR frames and UAV telemetry readings was achieved utilizing the computer's internal Unix time. During flights, the onboard computer was remotely controlled by an external computer to start and end data collection, which in this study was a Windows 10 laptop hosting an Ubuntu 18.04.3 LTS virtual machine. In the field, the two computers were connected via Wi-Fi and communicated with each other based on Secure Shell protocol. This figure summarizes the connection and communication between all hardware components. I also want to share with you this picture, which was taken during New Year's Day in 2021. It was not easy for me to figure out the communications between all the components of the UAV-LiDAR system at all. In the picture was the living room of the apartment that I was living in at the time. I had two roommates, but luckily both of them were not in the apartment during winter break, so I got to use all the space. As you can see, it was a whole mess. LiDAR, UAV controller lying on the ground. UAV with Raspberry Pi on top, which was connected to display, mouse, and keyboard. In the far background, you can see the steel sheet for mounting all the components. I was also testing different designs for the 3D printed LiDAR plate to make sure it is light, but also rigid enough to not cause vibration to the sensor. That's why there were 4 holes on the plate. Additionally, you also see another drone with a dual RGB thermal camera payload, some calibration boards, and a fan heater. Those were for lens distortion correction for both RGB and thermal cameras for a crop monitoring paper that I planned but never got to officially work on. I collected tons of UAV imagery data of an apple orchard and generated tons of point clouds in different spectral bands. Hopefully one day I'll get to work on those data and get the paper published. So this was pretty much how my life has always been. When everyone else was celebrating on a holiday, I was working and struggling in a dark basement by myself. Let's get back to the paper. The problem of LiDAR data registration in this study can be decomposed into the registrations of N-1 pairs of adjacent LiDAR frames, assuming N LiDAR frames are collected. And the goal is to find out the optimal translational and rotational parameters of a 3-dimensional rigid transformation that registers source frame onto destination frame in every pair. Here Tx, Ty, Tz represent distances, while Rx, Ry, Rz represent angles. Given 2 adjacent aerial LiDAR frames of level agricultural fields, such as an orchard, mainly vegetation and ground will be captured in the point clouds, and the challenge of precisely aligning such 2 frames lies in the lack of distinctive point cloud features within LiDAR's limited field of view. Due to the complex structures and detailed surfaces of plants, the distribution of vegetation points can be substantially different between frames, even for a small UAV displacement. While observed ground points mostly consist of flat plains that do not possess unique geometric features, and LiDAR's nadir view does not allow potential landmarks such as tree stems and trellis posts on the ground to be properly observed as if in a ground-based application. Such characteristics of vegetation and ground points bring much uncertainty to an algorithmic point cloud alignment process and can lead to significant cumulative reconstruction errors when multiple LiDAR frames are registered. Here we have an example of a pair of adjacent LiDAR frames collected over an apple orchard with roughly a 5 cm displacement along x-axis, showing the randomness of vegetation point distribution and the uniformity of ground planes. Point color here represents relative height in z-axis within frame. ICP, or Iterative Closest Point, is a type of popular point cloud registration algorithm. Its variants have shown great potential for outdoor environments as they require no feature extraction. Generally, ICP iteratively minimizes an error function for point-to-point, point-to-plane, or plane-to-plane distances between two-point clouds. Certain ICP variants also utilize non-geometric information such as color to optimize point cloud registration. In the case of an agricultural field, a few point cloud preprocessing steps can be employed to potentially improve LiDAR frame registration. Ignoring randomly distributed vegetation points can help reduce noises and simplify the registration problem into the alignment of two ground planes, while colorizing point clouds with LiDAR reflectivity values might be beneficial in guiding LiDAR frame alignment, since bare soil and surface vegetation such as grass have different near-infrared reflectivity and can form unique ground reflection patterns. Nevertheless, significant challenges still exist for registering agricultural LiDAR frames, even using an ICP-based algorithm. First, the initial transformation of a registration is important for ICP to avoid local error minima. However, since the overall point distributions of two adjacent LiDAR frames are highly similar, ICP can completely fail to register two LiDAR frames when their initial poses correspond to an error minimum. Second, even if ICP is able to optimize the relative poses between two LiDAR frames along the LiDAR's horizontal field of view dimension, empirically speaking, it often performs poorly in determining the translational parameter along the LiDAR's vertical field of view dimension, as the point distribution along the dimension is simply too sparse to be helpful in guiding point cloud registration. To overcome the aforementioned issues, we proposed a GNSS-IMU-Assisted colored ICP algorithm, which approximated ground planes in boresight error-corrected, IMU attitude-adjusted LiDAR frames to be level, and selectively combined the translational and rotational parameters obtained from a colored ICP algorithm and UAV telemetry data, with the goal of compensating the ICP algorithm's weaknesses along the LiDAR's vertical field of view dimension with GNSS location and IMU orientation information. This figure provides an overview of the proposed algorithm. There are three major assumptions or application limitations of the proposed algorithm, which will be explained later. First, LiDAR frames are of a level agricultural environment. Second, parallel patterned features exist along the LiDAR's vertical field of view dimension. Third, UAV flight paths are straight and follow the parallel feature direction, and UAV flight altitudes are constant. By default, the coordinate systems of geography, the LiDAR and IMU of our UAV-LiDAR system, and typical point cloud viewing software do not match with each other, and axis redefining is constantly needed for data processing and point cloud viewing. For the rest of the video, we will assume the coordinate systems of geography, UAV telemetry, and LiDAR data have been redefined to match with the software coordinate system whenever necessary. Before LiDAR frame registration, boresight errors between LiDAR and IMU need to be first corrected to align LiDAR coordinate system with IMU coordinate system, which was achieved through this equation, where XR, YR, ZR are raw coordinates of a point in an axis-adjusted LiDAR frame. RB is a rotation matrix derived from boresight errors BR, BP, BY, and X1, Y1, Z1 are boresight error-corrected coordinates. Then IMU attitude angles need to be adjusted to align IMU coordinate system with geographic coordinate system, which was achieved through this equation, where RA' is a rotation matrix derived from IMU attitude angles AR, AP, AY converted from quaternions, and X2, Y2, Z2 are IMU attitude angle adjusted coordinates. Note, in the study attitude angle AY was not corrected and assumed to be 0 intentionally during LiDAR frame preprocessing, so that x-axis of LiDAR frames always represented UAV heading, which will simplify the calculations for telemetry-based parameters in the following steps. This picture shows the pre-processing of a raw apple orchard LiDAR frame to an axis-redefined, foresight error-corrected, IMU attitude angle adjusted frame. Point color represents relative height in z-axis within frame. The first step of LiDAR frame processing is to remove vegetation points from ground points, which was achieved through ransack-based point cloud plane fitting. The function was implemented in the Open3D library, which fitted hypothesized planes to sets of randomly sampled 100 points over 1,000 iterations to maximize plane inlier points below an empirically determined 0.3 meters distance threshold. The picture shows the vegetation point removal of an apple orchard LiDAR frame. Point color represents relative height in z-axis within frame. Since the LiDAR scanner reported diffused reflectivity values as integers ranging from 0 to 100, a contrast stretching was first applied to both frames to enhance reflectivity contrast using the maximum and minimum reflectivity values among a LiDAR frame pair as upper and lower limits to be stretched to 0 to 255, and then the grayscale reflectivity values are converted to RGB color space. This picture shows contrast-stretched colorization of an apple orchard ground plane based on grayscale reflectivity values. Point color represents near-infrared reflectivity. Since LiDAR reflectivity values can be influenced by scanner parameters such as laser wavelength, emission power, beam opening angle, system attenuation, etc., external factors such as distance, incidence angle, object surface composition and moisture content, etc., and atmospheric conditions, correction for these noise sources can potentially improve the reflectivity consistency and alignment accuracy of ground planes. However, considering the small UAV displacement between each pair of LiDAR frames, the limited LiDAR's field of view, the constant, low flight altitudes, and the short flight durations, no LiDAR reflectivity correction was performed in the study. Now let's talk about the colored ICP registration step, which is really the heart of the whole algorithm. The colored ICP algorithm was proposed by Park et al. And implemented in the Open3D library. What makes this variant special compared to standard ICP is that it locks point cloud alignment along the estimated tangent planes of points based on a joint geometric and photometric optimization. Basically, it is optimizing two things simultaneously. First, the geometric term, which measures the distance between points and their corresponding tangent planes, and second, the photometric term, which measures the difference between point colors and their corresponding projection colors on tangent planes, which in our case was the colorized point near infrared reflectivity. These two objectives are combined into a single objective function with empirically determined weights and optimized iteratively during registration. For the colored ICP to work well, we needed accurate normal vectors for every point, since normal vectors indicate the orientation of the local tangent plane at each point, and Open3D estimates them through vertex normal estimation. To have normal vectors that reflect accurate local tangent plane orientations, neighboring points of each point along both the LiDAR's horizontal and vertical field of view dimensions in a LiDAR frame should be considered. Since we want the tangent plane areas to be as small as possible so that the point cloud retains the most geometric detail, normal vector estimation of a point was completed by involving neighboring points from only two adjacent laser scanning lines. However, since the distances between a point and its closest neighboring points on adjacent laser scanning lines vary depending on the point's location along the LiDAR's horizontal field of view dimension, a range of search radiuses for neighboring points were utilized. The maximum search radius corresponds to a search area that covers 3 adjacent laser scanning lines for points at the farthest corner of a ground plane, while the minimum value is for points located at the center. The registration was optimized over multiple iterations, which was 6 in the study, with the search radius increasing by a fixed step from minimum to maximum at each iteration that depends on flight altitude. This figure here shows contrast-stretched, colorized ground points of a pair of apple orchard LiDAR frames. Point color represents near-infrared reflectivity. The upper LiDAR frame shows the minimum and maximum search areas are able to cover exactly 3 laser scanning lines for points located at the center and the corner of a ground plane respectively, while the lower frame shows neither of the minimum or maximum search area is perfect for all ground points and can lead to compromised point cloud geometric details. Hence, employing a range of search radiuses can be helpful for registration optimization. Since ICP can be very sensitive to the initial transformation, if the starting point of the source frame is at a local error minimum, ICP can completely fail to find the right registration. So instead of starting with 0 translation and 0 rotation, we modified the initial TX and RZ of the source LiDAR frame based on UAV telemetry data. TX here is the component of LiDAR scanner center horizontal displacement along the initial UAV heading direction, and RZ is the heading change between 2 adjacent LiDAR frames. For the following discussion, UAV is assumed to fly from LiDAR frame 1 to LiDAR frame 2, and corresponding data are denoted by subscript 1 and 2. The goal of registration is to align source frame 2 to destination frame 1. Given the latitude, longitude, altitude, and quaternion readings from the UAV, the northing, easting, and altitude of LiDAR scanner center are calculated through this equation, where RA is a rotation matrix derived from IMU attitude angles, AR, AP, AY, converted from quaternions, and LX, LY, LZ are lever arm offsets between LiDAR scanner center and GNSS receiver center, or ideally GNSS antenna phase center, and northing R, easting R, and altitude R are UTM coordinates of GNSS receiver center, or ideally GNSS antenna phase center derived from raw GNSS readings. The horizontal displacement of LiDAR scanner center between the 2 LiDAR frames is then computed using this equation, and the relative bearing from frame 1 to frame 2 in terms of latitude and longitude of LiDAR scanner center converted from northing and easting is calculated using this equation, where the relative bearing ranges from -180 to 180 degrees. The UAV headings of the 2 LiDAR frames are equivalent to the corresponding IMU attitude angles AY, which also range from -180 to 180 degrees. Finally, TX is calculated using this equation, which is used as the initial ICP translation parameter, and per right-hand rule, RZ is calculated using this equation, which is used as the initial ICP rotational parameter. The rest initial transformation parameters of the source LiDAR frame are all specified as 0. This diagram shows the calculation of UAV telemetry-based TX and TY given LiDAR scanner center displacement between 2 adjacent LiDAR frames, relative bearing, and UAV headings. The difference between 2 headings and TY in the diagram are exaggerated for illustration. In actual UAV flights with straight paths, heading 1 and heading 2 are almost identical, and TY is much smaller than TX. After executing the colored ICP algorithm with the modified initial transformation parameters, the returned translational and rotational parameter values are TX-ICP1, TY-ICP1, TZ-ICP1, RX-ICP1, RY-ICP1, and RZ-ICP1. As we discussed, the colored ICP tends to perform poorly along the LiDAR's vertical field of view dimension, so we do a telemetry-assisted adjustment to the translational parameters. Specifically, after adjusting TX to the correct magnitude based on the telemetry-based TX through this equation, TY is also adjusted accordingly through this equation to preserve the correct relative translation along the LiDAR's horizontal field of view dimension due to the existence of bore sight error. There is another interesting challenge specific to agricultural environments, what we named as the parallel pattern issue. In agricultural fields, crops are often planted in rows for management and harvesting, which form parallel geometric or photometric textures, while flying the UAV LiDAR system along crop rows can help maximize features along the LiDAR's horizontal field of view dimension for more accurate TY estimations. However, in practice, we observed that the colored ICP algorithm often returned a TX with incorrect direction, even though the value of TX in the initial transformation had been modified based on telemetry data. Our hypothesized theory was that for non-parallel patterns, it is less likely for the ICP algorithm to return a TX in the false direction, since that would correspond to a higher registration error than the correct TX direction, regardless of how the algorithm tries to optimize registration. While for parallel patterned features such as rows of soil and grass, their registration errors in both TX directions can be similar, thus leading to a higher likelihood for the ICP algorithm to return an incorrect TX direction. This figure here illustrates false TX direction has a bigger influence on registration error for LiDAR frames with non-parallel feature patterns than the ones with parallel feature patterns. Boresight errors are assumed to be 0. To correct for that, using the telemetry-based TX as a reference, when the direction of TX returned from ICP is inconsistent with what telemetry says, we flip it to the correct direction. And due to the existence of Boresight error, when TX is flipped, TY is also flipped accordingly to maintain parallel feature pattern. This figure here shows how the relative pose of LiDAR frame 2 changes with respect to frame 1 after telemetry-assisted adjustment, assuming the relative bearing follows parallel patterned features and UAV headings of 2 LiDAR frames are the same. In the diagram, each LiDAR frame is represented by a single laser scanning line, and BY and TY are exaggerated for illustration. The final step is telemetry-based error filtering. To filter out erroneous or suboptimal registration results from the colored ICP algorithm, telemetry-based TY and RZ are also used as thresholds. The underlying concept is straightforward. For a pair of adjacent LiDAR frames from an ideal straight path flight, TY and RZ should both be close to 0. So if the ICP algorithm returns TY or RZ with absolute values larger than the telemetry-based ones, we consider the algorithm has failed to find the right registration for those parameters, and we substitute in the telemetry-based values instead. Telemetry-based TY is calculated using this equation, and the final transformation parameters are then assembled from a combination of ICP outputs and telemetry data, as shown in these equations. Assuming the coordinates of a point in LiDAR frame 2 is x2, y2, z2, the transformed coordinates xt, yt, zt of the point after registering LiDAR frame 2 to frame 1 are calculated through this equation, where RF is a rotation matrix derived from the rotational parameters Rx final, Ry final, Rz final. The registration of multiple LiDAR frames is achieved by repeating this whole process for every pair of adjacent frames sequentially. This figure here shows an example of an apple orchard point cloud consisting of 480 LiDAR frames registered by our proposed algorithm. Point color represents near-infrared reflectivity, and here is a pseudocode of our proposed algorithm. Now let's move on to the Peachtree parameters estimation experiment, where we put our proposed algorithm to the actual test. The developed UAV-LiDAR system was deployed at the Penn State Horticulture Research Farm in Pennsylvania Furnace, Pennsylvania. A roughly 65-meter-long peach tree row, whose coordinates are listed here, consisting of 11 trees and 3 different varieties, was chosen as the target. The reason for choosing this particular row was that the ample spacings between the trees allowed individual tree structural parameters to be easily measurable during ground truthing and extractable from point clouds. 3 tree parameters were selected as the metrics for evaluating our algorithm's performance, and 1 for each orthogonal dimension: WA, or tree crown width along tree row direction, WP, or tree crown width perpendicular to tree row direction, and H, or tree height. This picture shows the 3 parameter dimensions relative to the peach tree row. Manual measurements were taken using a tape measure on June 1st of 2021 as ground truths. Crown widths were measured as the horizontal distance between the 2 farthest points of a crown, while tree heights were measured as the distance between the tallest point of a tree and its vertical projection on the ground. In the pictures were my lab mates and buddies, Tyler and Omid. At the time, both of them were master students. Tyler was doing some UAV-based tree flower detection research using YOLO, while Omid was doing apple sizing research using a customized ground-based camera LED system. Both of them helped me a lot during my research, since I always needed a visual observer whenever I flew drones, and I needed someone to help carry the big drone case with me. I believe Omid has a degree from Carnegie Mellon, so he was very technically sound, and I always thought he should work in industry because of that. I think I got into Linux because of him, and he also tried to help me set up ROS on Raspberry Pi for this study, although we failed miserably. I still remember I had an intentionally stupid debate in my office with him about if I can have a shortcut on my desktop in my Windows computer to so conveniently do what I need to do. Why would I need to type up complicated commands in terminal in a Linux machine using a primitive keyboard? Omid specifically told me he didn't want to show his face in the pictures. That's why he was facing away from camera in both pictures. Also, as you can notice, both of them were wearing masks, so we probably collected the field data during COVID. I believe that day I bought frozen yogurt for all of us after the field data collection. I remember we ate in the parking lot. Tyler was asking me what the right ticker for Tesla stock was, because he registered an account with Webull, and it was giving away free stocks for all new users. I think I also got to know my favorite frozen yogurt flavor tart because of Omid on that day. Just some good old grad school day memories. I hope both of them are doing well. On the same date, LiDAR data from 3 autonomous UAV flights were collected. All 3 flights had the same UAV flying speed of 1 meter per second and an identical straight flight path along the tree row direction. The flight altitudes were set at 10, 20, and 30 meters respectively to test the performance of our proposed algorithm under different LiDAR point densities. Approximately 1,100 LiDAR frames were collected during each flight. For data processing, the LiDAR data from each of the 3 flights were registered using 2 methods for comparison. The first method was GNSS coordinate and IMU attitude angle-based georeferencing based on this equation, which was implemented in MATLAB. The second method was our proposed GNSS-IMU-Assisted colored ICP algorithm implemented in Python 3.8.5. The bore sight errors between the IMU and the LiDAR of our system were estimated using the orchard ground as a calibration field, while the lever arm offsets between the GNSS receiver and the LiDAR were manually measured. After obtaining a registered point cloud of the peach tree row, the tree row direction was first determined by segmenting tree points from ground points and fitting a line to only the tree points. For easier individual tree parameter extraction, the peach tree row point clouds were rotated along z-axis to align the fitted lines with the x-axis. Then individual trees were manually cropped out. For parameter extraction, WA was the farthest distance between 2 tree points along x-axis. WP was the farthest distance between 2 tree points along y-axis. H was the distance along z-axis between the tallest tree point and the median height of ground points within a 10 cm by 10 cm area centered at the tree point's vertical projection on the ground. The accuracies of extracted tree parameters were analyzed in terms of R² and RMSE in comparison to manual measurements. This figure here shows an illustration of individual tree parameter extraction from a peach tree row point cloud. Point color represents near-infrared reflectivity. Now let's look at the results. This figure shows the extracted peach tree parameters including WA, WP, and H from point clouds collected at different flight altitudes and registered by GNSS and IMU-based georeferencing and our proposed colored ICP algorithm in comparison to manual measurements. Overall, the results showed that our UAV-LiDAR system was a promising instrument for general plant parameter estimation, even without differential GNSS. Solely relying on GNSS and IMU, the system estimated tree crown widths with RMSEs ranging from 0.09 to 0.43 meters depending on flight altitudes, while tree height estimation RMSEs fluctuated in a smaller range of 0.05 to 0.18 meters. With the help of our proposed colored ICP algorithm, peach tree crown width could be estimated with RMSEs no more than 0.2 meters, while tree height could be accurately estimated with RMSEs no larger than 0.06 meters. In the study, our methodology for extracting tree parameters was by using the farthest points along WA and WP dimensions and the tallest point along H dimension of a tree point cloud to represent crown widths and tree height, so that the degree of point cloud misalignments could be directly reflected in the estimated tree parameters. For optimal tree parameter estimation, the point cloud percentile method, which was proposed in my very first paper, can be effective in reducing estimation errors. For example, instead of using the distance between two farthest points, which is equivalent to the distance between 0th and 100th percentiles, a 0.5th to 99.5th percentile range could improve georeferencing-based WP at 30 meters to an R-squared of 0.75 and an RMSE of 0.16 meters, while a 0.1st to 99.9th percentile range could improve the proposed algorithm-based WP at 30 meters to an R-squared of 0.91 and an RMSE of 0.09 meters. For GNSS and IMU-based georeferencing, performance generally decreased with altitude. This makes sense because point cloud misalignments caused by IMU attitude angle errors increase linearly with altitude. That is, the same angular error in degrees causes a larger positional offset the higher up the LiDAR scanner is. This image illustrates the same IMU attitude angle error can cause larger point cloud registration errors for high-altitude LiDAR data than low-altitude LiDAR data. Therefore, parameters extracted from high-altitude tree point clouds tended to be less accurate. Although wind speed could be higher at high altitudes during data collection, which would cause more sensor synchronization errors when IMU readings changed sharply, we do not think it was a major factor that caused the lower accuracy of georeferenced high-altitude LiDAR point clouds. Another interesting observation was that the WP estimations were consistently less accurate than WA, and we believe it was mainly because LiDAR points were much denser along the WP dimension than the WA dimension. For example, at the 30-meter flight altitude, the average distance between the adjacent laser scanning lines along the LiDAR's vertical field of view dimension in a LiDAR frame was roughly 1.1 meters, while the average distance between two adjacent points on the same laser scanning line was approximately 0.3 meters, as illustrated in this image. This means the LiDAR scanner had a much higher chance of capturing reflected points near the true widest crown boundary along WP than WA. As a result, the likelihood of having LiDAR points being falsely registered to positions wider than the tree's true widest crown points along WP dimension was significantly higher than WA dimension. In terms of H accuracy, georeferencing delivered similar results for the 10-meter and 20-meter flights, yet the 30 meters results became significantly less accurate. Two outliers existed among the 30 meters estimations, which indicated the performance instability of low-accuracy GNSS receiver and IMU. By removing the outliers, the corresponding R-squared and RMSE could be improved to 0.97 and 0.05 meters, which are similar to the 10-meter and 20 meters results. In comparison, the proposed colored ICP algorithm either outperformed or delivered similar results to the georeferencing method for all tree parameters at all altitudes. For example, improving WA RMSE up to 33%, while for the only two scenarios where our algorithm did not outperform the georeferencing method, namely R-squared at 10 meters and RMSE at 20 meters, the results from both methods were comparable. Improving WP RMSE up to 58%, and improving HRMSE up to 67%. Our proposed algorithm delivered consistent WA estimations at all altitudes, which theoretically should be close to georeferencing results since they were based on telemetry-based TX, and indicates the validity of our method of decomposing displacements between LiDAR frames along UAV heading direction. Similar to the georeferencing method, the estimations of WP by our algorithm also decreased with altitude, However, it was more likely due to the lower density of LiDAR points, or the less detailed photometric or geometric texture in a LiDAR frame along the LiDAR's horizontal field of view dimension, since distances between adjacent LiDAR points increase with altitude. The stable and accurate H estimations across all altitudes by our proposed algorithm implied that level field ground planes in LiDAR frames were very helpful in determining the transformation parameters TZ, Rx, and Ry. Meanwhile, it is also because of the reliance on ground planes. Large tree size can be a factor that impacts the performance of our proposed algorithm, considering dense vegetations can prevent laser beams from reaching ground. When UAV flight altitude decreases, the ratio between blocked ground area by large trees and total ground area within a LiDAR frame increases, leading to fewer available geometric and photometric point cloud features for the colored ICP algorithm. However, when flight missions are conducted under non-extreme altitudes, such as larger than 10 meters, for fruit trees, such as peach trees, tree size should have minimal effects on LiDAR frame registration accuracy. In the study, we manually measured lever arm offsets and calibrated bore sight angles in a calibration field. While various calibration techniques have been proposed in literature and can be adopted as alternative methods. In terms of point cloud registration accuracy, lever arm and bore sight calibration imperfection mainly cause translational errors rather than rotational errors. Regardless of LiDAR frame initial positions, the colored ICP algorithm will likely return proper rotational parameters in all three dimensions for LiDAR frame pairs by aligning the segmented ground planes, while imperfect bore sight calibration will introduce translational errors to all three dimensions of LiDAR coordinate system during telemetry-assisted TX and TY adjustments. On the other hand, uncalibrated lever arm offsets will lead to less accurate telemetry-based TX and TY calculations when IMU attitude angles between a pair of LiDAR frames on the same dimensions are not identical. However, a bigger influence will occur for X dimension than Y dimension in the final registration, since telemetry-based TX determines the magnitude of TX final, while telemetry-based TY is only utilized as a threshold for filtering out TY outliers from the ICP algorithm. For straight-pathed UAV flights with constant speeds, ideally, IMU attitude angles of LiDAR frames should remain constant, yet in reality they fluctuate within narrow ranges. Given two consecutive angles on the same dimension, the current angle can be either larger or smaller than the previous angle. Consequently, calculation errors of telemetry-based TX and TY due to uncalibrated lever arm offsets can be on either direction of the dimensions and would roughly follow a normal distribution centered at 0. Among the limited studies in the agriculture area that were somewhat similar to our current study in Nature, Dami et al. In 2021 built a customized UAV-LiDAR system with DJI Matrice 600 Pro, Velodyne Puck, and Jetson TX2 utilizing DJO SDK, and estimated wheat plot heights using georeferenced point clouds with errors ranging from -0.5 to 1.05 meters depending on their point cloud height extraction methods. Sofonia et al. In 2019 used the commercially available SLAM-based LiDAR payload hover map at a 30 meters flight altitude to estimate sugarcane block heights, and obtained R-squared values of 0.91 and 0.93 for max and mean block heights. In comparison to the results of the two studies, although different crops were involved, our proposed algorithm demonstrated its potential of being an inexpensive alternative to DGNSS for accurate plant structural parameter estimation. For future research, there are several aspects of the proposed algorithm that could be improved upon or built on. First, the current algorithm was limited to single-pass LiDAR data from straight-path flights. For flights with curved paths, the ICP algorithm tended to register LiDAR frames to paralleled positions along LiDAR's horizontal field of view dimension and couldn't reliably recognize the rotation along Z-axis, which broke some of the key assumptions for the telemetry-assisted adjustment and made our proposed algorithm fully reliant on telemetry-based RZ. Although completely replacing the colored ICP algorithm-based RZ with telemetry-based RZ could be a potential solution, our experiments did not suggest it was superior to georeferencing. For multipass LiDAR data, one potential solution would be to first reconstruct individual single-pass point clouds, and then merge overlapping data from different passes with advanced algorithms that utilize deep learning-based point cloud descriptors. Since our preliminary tests did not indicate traditional point cloud registration algorithms, such as ICP, could complete the task well for agricultural fields. Strip adjustment is another potential direction for multipass data registration. Image-based ranging techniques like structure from motion could also generate depth maps and help improving registration, although they require additional sensor payloads such as cameras. In terms of terrain, there are three aspects that can influence the algorithm's performance. First, flatness. Terrain flatness determines whether ground points in a LiDAR frame can be reasonably approximated as being on a single plane. For terrains with slight curvature, increasing ransack inlier distance threshold can still allow ground extraction. Compared to flat terrains, curved terrains also contain richer geometric features that assist ICP-based point cloud registration. However, when in-frame terrain curvature is significant, alternative methods such as reflectivity thresholding might be more effective in separating vegetation points from ground points. Second, surface evenness. Rough terrain surfaces are often absent in well-managed farms, such as orchards, yet they might have complicated geometric feature patterns that are beneficial to ground plane alignment. Third, slope. For slope terrains, if ground points in LiDAR frames can still be approximated as planes, the proposed algorithm-based TZ might be proportionally adjusted according to the difference between TX ICP1 and telemetry-based TX after telemetry-assisted TX and TY adjustment. With that being said, more research is still needed to verify the performance of our proposed algorithm under complicated, rough landscapes where in-frame ground points have too much height variations to be treated as planes. In terms of expanding our proposed algorithm into a SLAM pipeline, when a large quantity of LiDAR frames is being registered, issues such as cumulative registration errors or drift can be significant, especially when LiDAR looks at a small area during low-altitude flights. Loop closure detection is an essential and effective component in SLAM algorithm to correct accumulated drift. However, the lack of distinctive landmarks in agricultural fields makes this challenging. As potential solutions, GNSS coordinates might be helpful in confirming global data association when UAV travels back to previously visited locations, while placing highly reflective artificial targets in fields could be another way to guide a potential SLAM algorithm on differentiating similar-looking LiDAR frames. For a faster program execution, by lowering the iterations of ground neighboring point search from 6 to 1, such as only searching with the minimum search area, the average registration time for a pair of adjacent LiDAR frames could be decreased from 1.2 seconds to 0.2 seconds, at the cost of potentially a small or minimum registration quality reduction. In conclusion, due to the unique nadir view of LiDAR and the lack of distinctive environmental landmarks, aerial LiDAR point cloud registration for agricultural fields could be challenging for pure algorithmic approaches. This study explored a low-cost solution to accurate point cloud alignment utilizing a colored ICP algorithm and location and orientation information from a UAV's built-in GNSS and IMU. In terms of peach tree crown width and height estimation, the performance of low-accuracy GNSS and IMU-based georeferencing tended to be unstable and decrease with flight altitude, while our proposed algorithm provided more consistent estimation results for all tree parameters and flight altitudes with higher accuracies in most cases. Despite its limited adaptability, the proposed algorithm could potentially serve for future studies on developing robust SLAM algorithms tailored for agricultural environments. Nevertheless, research is still needed for generalizing the algorithm to be able to register multi-pass LiDAR data of more complicated topographies. This paper was arguably one of my most technically complicated work to date. Even I myself now had to read the paper carefully and contemplate in order to understand my thought process back in the days. To be honest, I have no idea where and how I got the inspiration and creativity to develop the algorithm, and sometimes when I think about the paper, I even laugh and wonder about that, because it was designed for such a specific problem. If I remember correctly, I was right in the middle of a near-death health crash when I was writing this paper. Can't eat, can't sleep, can't breathe, can't sit up, can't do anything. My whole body was failing on me. My lower back pain was so bad that I had to sit on the recliner that my roommate picked up by a dumpster and constantly adjust the backrest angle to temporarily alleviate the pain so I could write a few words. I remember I was half conscious on bed since I haven't slept well for many days when I heard a new email alert. I got off bed, checked the email. It was my committee member, Dr. Bolkas, sending me his comments on the first manuscript draft. I then just started to reply to his comments and revised the manuscript using my barely functioning brain. That was how the paper was done. The proposed algorithm was far from being perfect. At the time, it was only designed to work on single-pass LiDAR data, and I remember it was not working very well for multi-pass data. My code was also rather unprofessionally written and disorganized, with a mixture of Python and MATLAB. That was why I didn't open source the code, since it would be a challenge and a big task for me to clean up the code and make it user-friendly. Luckily, the core algorithm, colored ICP, has open-source Python implementations in the Open3D library, and I have provided the pseudocode, so hopefully it is not too difficult for other researchers to replicate the algorithm. Just to let you know, starting with this video, I will use AI to clone my voice and read through the scripts that I will prepare for my future videos instead of recording myself to save some time. Maybe it does not seem like it, but it is extremely time-consuming for me to prepare every single video. I need to read through the whole paper, understand all the details, make a very detailed animated PowerPoint presentation, write a voiceover script, record myself reading through the script in FL Studio, edit out all the errors, audio glitches, and adjust the pacing for all the words and sentences. Upload the edited audio to Adobe Podcast for background noise removal and cleaner voice. Export the PowerPoint into a video. Edit the video in After Effects by manually splitting the whole video into hundreds of layers for every single animation, adjusting each layer to match the animation with the audio, and freeze the last frame of each layer if necessary to fill the gaps between layers after timeline adjustment. I am certainly working on automating my workflow wherever I can to improve my efficiency. I have written scripts to auto-split video and fill layer gaps in After Effects. Using AI voice is my next step. But frankly speaking, current open-source TTS models are far from being perfect for long texts, and I have made thousands of cuts to remove mispronunciations, glitches, and adjust the pace of the current audio, which is still extremely time-consuming and costed me too many weekends. I am spending so much time making videos for all of my old publications that I really miss doing new research and writing some new papers. By the way, I am very proud to say that I have factually proven to myself that I no longer need to seek external validation anymore. At the time of me writing the script, my last paper video precisely has 0 views, yet I still made another one which I expect would still get 0 views. Despite I dump an absolutely massive amount of my energy and time into making these videos, they do not get promoted by YouTube's algorithm at all, and there is no audience for them. This is also true for the videos on all my other channels universally. It is impossible for me to keep making these videos if my goal was viewership, because so far, my return on investment was basically 0, and it would be insane for me to keep doing the same thing but expect a different outcome. The only sustainable way for me to grind out these paper videos is by stripping away my desire for external validation, such as views, subscriptions, likes, or comments, so that when they do not happen, they do not affect me, and I do not become a slave of them or the YouTube algorithm. I make my videos for the sake of making them, and they are the legacy of me, or the character that I am playing in this life, when, to this world. With that being said, it is still possible for me to promote my videos somehow one day in the future, because I believe they absolutely deserve to be seen by a large audience. and the world needs long-form intellectually challenging videos more than short-form entertainment videos. I'll see you in my next paper.